Thank you for the introductions. And my name is Kihwan Kim at the Department of Physics in Tsinghua. And first of all, I greatly appreciate the organizer of ICQC and also the Professor Kim to invite me to talk about our research with trapped ions. Also, I'm happy to see the Sujan gave some overview of also the Sandia's works. And anyway, today we will talk about our effort to scale up the trapped ion system, mostly extending dimension to 2D crystals. So that this is a brief my outline, and then we are working on trapped ion systems. As you know, this is one of the leading platforms for quantum computation and quantum simulation. So in terms of coherence time, the logic gate fidelities, and the number of entanglement, in our field, the people are really pushing a lot. And in Tsinghua, we also to contribute in this area. So about the coherence times, we extend to over hours. So we have to admit that we didn't make this qubit better. We just observe already good atoms, qubits, coherence. That's what we did. This is currently limited for technical noises and so on. But fundamentally, we don't see any coherence time-wise limitation. And also, we did effort for the improving the logic gate fidelity. And so that we are pretty close to the world-leading levels. And about the number of qubits in the entanglement and universal quantum computation and so on. So be in some following level. And then also the simulation-wise, we also think about how we can push this field more and more. So today, really, I'm going to talk about our main effort to scale up our systems. So as you know, the trapped ion system roughly looks like this. So we are dealing with individual atoms, and so the nearby there is nothing. So we first build a vacuum system, so the pumping out every atoms as much as possible, and then inside we have rotating electric field traps called the pole trap, and then in the middle, the individual atoms is trapped like this linear chain, linear string, and since they are charged particles, they are repelling each. So we collect the fluorescence of atoms, and then we do see this. So the trapped ion quantum computation, this individual qubit, individual atom, so the ground state 2 level, we map to qubit, and then choice of hours of ytterbium. It has very nice properties, qubit. That's how we can observe very long coherence time. And then this qubit is inside harmonic potential, and then, for example, the center of so all the atoms together, or it's stretching and so on. So they have a certain type, and we can address with the larger frequency, also the smaller than trap frequencies and so on. So this is the basic ideas of our trapped ion system. Single atom has one qubit, and then this qubit in the harmonic trap, there has some bunch of collective vibrational mode. So in this of 7 ion, we have a 7 vibrational mode, and so on. So this is our whole system to deal with. And before I'm going to talk about qubit or 2D crystal experiment. I briefly want to introduce our another effort to scale up. So instead of dealing with the qubit itself, we are using this vibrational mode as a quantum bot. So for example, when you have this 5 ion, all sure individually, in that case, we will have this 5 different vibrational collective mode, something tilting like that for zigzag shapes and so on. And each one we can consider as a harmonic oscillator. And here we can prepare any number of phonons deterministically, and also the detection also deterministically. So we are thinking about using this trapped ion system, putting some beam splitting operations and so on, something like this photonic system that may be able to show some quantum advantages. So in our system, we think the advantage is so we can prepare and detect deterministically, and then each beam basically no loss. So while we scale up the system as big as possible, we may not have a problem that the photonic system has some difficulties. So we are pushing this one up to now 4 mode situation, and we believe so when then inside as the number of ions increases, we will have a proportional increase in vibrational mode. So each one we can control through the single ion, the applying laser beam on the single ion. So we think we are reaching, we have a strong chance to reach the level for the quantum advantage through this method. Okay, so much for this. So now I'll just briefly introduce how we operate trapped ions for the computations and simulations. So the idea is first, when we have this linear chain of ion, and we don't cool the whole system, though Susan already mentioned you can put in the cryostate environment. We only cool these atoms itself by using laser beams. And then each qubit we initialize to the spin's down state, and then we do a bunch of operations, and then at the end we detect. So if our quantum state is up, then we can see the atoms. If our quantum state is down, we don't see. So at the end of operation, we will have this kind of the result in the camera. So we just bright ion is up, dark ion is down state. We can simply discriminate the states. And then for the single qubit operation, there are several ways, but the simplest way that we can imagine is we just individually address one of the ion that we are trying to operate, and then this laser just requires has a 2 frequency, is matching exactly same to the qubit frequency. In that case, we can do the nice single qubit operation, and this is the result of single qubit operations. And then for the 2 qubit operation, we have to do something more. So far, all these qubits are not talking to each other. They are all levitated atoms. We are using hyperfine levels of this as a qubit, but they each other. So when we make some qubit, we need to use vibrational mode, such that this laser is specifically designed that depending on spin, so if the spin is up, then there's pushing up. If the spin is down, and then the pushing down. So we apply the laser beam with this kind of spin-dependent force level. That if we think of, then this the 2 atoms naturally will be excited. And then when we have this vibrational excitation, and this quantum state will get certain phase. Configuration is different. We will not see any the movement, then the no phase, and so on. So eventually, depending on spin configuration, we will get certain phase or no phase. So this one, if you write in terms of Hamiltonian, and then it's formulated like that. So the up case remains, up down cancel out, and so on. So naturally, to the spin interactions. So this is how it works. By using spin-dependent force, using specific vibrational mode, we can create effective spin-spin interaction that's basically equivalent to 2-cubic gate. Especially, this phase is pi over 4, that's entangling gate. And in this kind of things, we can understand as this kind of vibrational level diagrams, qubit, and when we have a one central mass mode, by applying the laser beam detuned array, we can create spins and vibrational mode coupling, and then the time evolution of this Hamiltonian. Ultimately, we disentangle all the vibration and the qubit coupling and the remaining spin part. So that's some mathematical description of what we are doing. And then this one is quite simplified one. So our system has so there are a lot of vibrations. There are axial vibration and the transverse vibrations and so on. So it's not that simple problem that we deal with a single vibrational mode. So the Hamiltonian wise, we have the qubit part and every qubit connecting to every part. So it's quite a complicated situation, but we have some way to deal with this time evolution properly. So I believe Professor Taeyong may say more about the details. So basically, we can disentangle all the qubit and the vibration, and then still remains this spin-spin interactions. That's how typically we do the trapped ion 2-qubit gate. That's also, I believe, what Sujan mentioned is more or less done this way. And recently also we modified these schemes. Instead of operation, we applied thing simultaneously, and then we can create simultaneously all possible types of operation. So you can track that. So one of a strong point is every qubit is connecting to every other qubit for the full connectivity. You can achieve all the possible pairwise operations, or by just simply one-time operation, like we demonstrated. And so either way, so this is a basic idea how we put the quantum gate on our trapped ion systems. And so this approach is the small networks with the merit, and also we point to pushing this one. So basically, n number of atoms by using the called multi-device, just specifically control the laser powers and the phase and also duration and so on. So we realize a specific 2-qubit gate for any pairs or just, all of them simultaneously. And so this is the IonQ's main approach. So people are pushing really these directions a lot. And also this kind of gate scheme, we can also apply to the quantum simulations. So this same spin-dependent force. So if we just apply the tuning level, and then as you see, we can effectively this kind of spin-spin interactions for every pair. So in that case, we can have some kind of at the most dipole decay types of is spin-spin interactions. And this scheme works really well. So the I also did with Chris Monroe, and then up to 10, and then 14, and even the 50 ion levels. People try to do a lot of simulation of this Ising index, spin-spin interactions. And so this is pretty well developed field. And then now I'm just introducing what are trying to contribute in these directions, especially for the 2D, using the 2D ion crystals. So the idea is in order to have the scaling up, one of the current major approach in IonQ and many other teams is using linear chains of ions. So with the cryostate environment, the Chris Monroe's groups push over 100 atoms and so on. And but we can naturally feel about how much we put. So can we put 1,000 atoms in linear chain or 10,000 atoms in linear chains and so on. So what we are considering is how about making a two-dimensional trap system. So these groups using a panning traps that has very fast oscillation already have this kind of two-dimensional crystal. But this is rotating really fast, so it's not that much favorable for individual controls and so on. And anyway, not necessarily this perfect two-dimensional geometry, but if we think about just two more just linear lines in the trap, and we can immediately see the 50 ion system can be 150s. And if we can put a similar layer, we can feel this scaling up the number of qubits in a trap ion system looks much more favorable. So this is a general intuition. Surely compared to 1D geometry of ion, maybe by using 2D crystal, it should work much better. And then also you can imagine the trapped ion system is very good for fully connected interaction between ion qubit. And then the people already saw the over 30 ions. Any pairs of ion can be as strongly interact as nearest neighbors. But it will still hold to as many ions, like 10,000 and so on. So that's all question. But if we can put together a structure, so let's say the 100 ions fully connected may be possible, but if we make a 10 by 10, and then because we are using the level, so this full connection is much easily achievable. And also one of the problem is whenever make a long ion chain, we have to lower the XR as low as possible. In that case, the XR frequency is a problem, but the two-dimensional structure we don't need to do. We don't need to lower XR too much. We can keep the pretty high frequency as we like. And also, it's very natural to do some surface code types of fault tolerant the realization of quantum computation, and also it's very good for candidate for 2D materials and also optimization problems. So as you know, recently we saw a lot of 2D material also in terms of quantum magnetisms appearing. So people found a pretty new material in the 2D layer, and then the study about these materials and so on. And when our ion system in 2D crystal it's very natural to simulate this kind of system. And moreover, this in the morning, we can also mention that the ground state of this kind of quantum magnetism related to the optimization problem. So, for example, if we have some kind of Ising, and then this is not the 2D case, and then it's related to MP hard problem, and then also it can be also contain the solution of traveling salesman or satisfiability problem or XCOD that Professor Jeogan mentioned and so on. So this two-dimensional crystal is a very interesting platform to pursue. And especially in terms of this optimization problem, people the pretty long time ago, compared to the method, if we use quantum simulation, quantum annealing, and then it may have some potential to show outperforming the classical computer. And that's why DRAM system, a lot of Gutenberg atoms, also the benchmarking and this kind of optimization problems as well with their hardwares. But here, one of the important requirements is the spin-spin connection should be all-to-all. Not nearest neighbor is not enough. I would say the entrapped ion system, we have this fully connectivity there. So it's natural to realize such a system. And then we can have this interaction-wise type of FM, AFM, all exist pretty controllable way. So it's very nice to do. But if we do the 2D ion crystal and the quantum computation, then we have naturally this full connectivity and also the FM, AFM, and then any interaction geometry can exist. But the problem that the trapped ion system that not allowed to do this one is basically we have some called micromotion problem. So because of that, we see that if there's only a linear chain, we don't have a micromotion. But outside the plane, we have a serious these oscillations that degrade the power of quantum operations. And so another solution is the panning traps, but they not able to do this individual control because of rotation, and also this one has some difficulty of making the single qubit operation and the spin-spin interactions together. So although the spin-spin interaction demonstrated 10 years ago, so far it's not yet achieved. And then by using trap, people have very sophisticated trap, but it seems very hard to get these two-dimensional crystals working. And one of the inspiration for us was by using some kind of axially squeezing trap, and then you can avoid this micromotion problems. And so let me explain soon. So we inspired by this one, we developed 3-layer traps such that our crystals or micromotion with resistance perpendicular to our reference. So as you can briefly see, so all our micromotion in this plane is vertical, but the laser beam is perpendicular, so we don't see any micromotion problem. That's our simple intuition. And then through that, we apply the laser beam, see the vibrational mode really well. So we thought it's a pretty good scheme to pursue. Some problem. Anyway, let me continue. So here, we have some. We need also the rapid cooling. So we do the EIT cooling developed, and then we applied this automatic quantum simulation idea. So preparing the single state finally automatically change to interesting Hamiltonian and detect. And so in this approach, we also developed some fast controls and so on. But we finally see even though there is a serious micromotions there with our approach, indeed this outside ferro anti-ferro interaction, indeed we can get the result as we expected. And also we just push this one as much as possible. So for 7 ion, different from the linear chain, we do see, so we have some 7 ion, some specific vibrational mode, especially here. And then everywhere is ferro. So we have a more or less a similar situation that we expected. And surprisingly, we just see that this works really well as we expected. And so here, as you see, we do see some is ferro, some is anti-ferro, all control exists. And then so far by just tuning the laser beam in different direction, and then we do have a different interaction geometry, and the final state looks like this straight stripe phase. And also the other tuning, we will have a different interaction geometry, and then the final ground state is half bright, half dark. That kind of state also observed. And we just question about this is just statistical mixtures or really the quantum coherence exists. So the one of the way to test is with ended up derivative simulation and the bring it back. In that sense, we do see most of the coherence part observed. So our simulation is really works in quantumism, and also we are considering some kind of phase transition we may connect, and then the pushing to the as much ions as possible. So we are quite excited that this system indeed really works, and with that, let me conclude our works. So in the 3D crystal system, also we can do some quantum simulation, and here we have a ferro, anti-ferro, all controlled, and then also we have a full connectivity exists. So we are pretty excited to scale up this way. I believe better than one this system, and also eventually we may need individual controls. With that, thanks for your attention.
Thank you for a really nice talk. We had around 3 minutes left, so and session is open for question. Is there any questions? Yeah, there was a little bit of network issue, so your voice was really breaking up. Yeah, let me give you one question about your 3D crystal. I think this trap geometry is really interesting. And I wonder how much controllability you have about the kind of like the ion configuration and like the distance between ion and like the geometry of the ion, something like that.
Thanks for really good questions about it. Can you see the slide as well? I'm not sure you can slide about the traps.
Yeah, we are looking at it.
Okay, thank you. So our trap itself is pretty much simple. It's not that much different from the traditional trap. The only difference is it has 3 layers to avoid the micromotion problem. And then the controllability-wise also not that much. We basically create the pancake types of potential, and then just each direction's frequency we can control, and then also we can rotate this axis by front and back side of traps, electric voltages. Other than that, we don't have a much degree of freedom of individually controlling all the ions. Just overall, we create the potential that we like, and then put the number of ions as much as we like.
Yeah, thank you for the answer. There's one more question from the online, which is the if you move on from 1D chain to 2D crystal, he expect the like noise model will be different from the 1D crystal. Could you explain a little bit more about it?
Noise. So that's a really good question that I didn't fully think about it. So the in terms of say so far in terms of noise model, so the noise our case mostly from the cubic noise itself, and then we are still using vibrational mode. So noise from the vibrational mode. So the cubic noise wise, it's 1D or 2D, it doesn't matter. Just the qubit is not interacting with other environment much. So the vibrational levels of noise can be a problem. So we do see our current trap has much huge hittings than the linear chains of ion. So that's we are seriously working on it and try to several ways to suppress this hitting levels of noise. And then I guess the question is about when we relate to the simulation, maybe because of 2D geometry, some kind of quantum fluctuation produces some kind of different types of noise. That's really interesting question, but we didn't yet explore that kind of because of interaction is 2D geometry. There will be some kind of different of this quantum magnetism case. Some different noise is not, we are very interesting to know about, but not much for now. Yeah.